Well, hey guys, welcome back to the bench. Today I'm going to talk about powering your op-amp circuits with a single supply. Well, if you're familiar with op-amps, you know they usually require a positive voltage and a negative voltage relative to their circuit ground. But there is a way you can power them up with a single supply, such as just one 9-volt battery. And we'll take a look at the different methods and do some demonstrations later in the video. Now there are catches and disadvantages of doing this, but if you look out for those pitfalls, it works pretty good. Okay, the first supply rail splitter is the passive design. It's called that because there are no active parts. It's pretty simple. You have your power supply going in here, and that runs through two resistors of the exact same value, and at that middle point will be a voltage that's 1/2 the supply voltage. Then you have these capacitors that are also connected at the center, and one to each rail. Those act as power reservoirs for your circuit, and we'll explain that in a little more detail. So now you have a common point, a negative voltage, and a positive voltage. You might say, well, how do I get a negative voltage from a battery? You see, you might use this battery as your power input. How are you getting a negative voltage? Well, what you're doing is just measuring from a different point. So it's all relative to the point you're considering your common or your ground. So this is called the virtual ground, the center point. And this voltage is negative relative to that, while this one is positive. So that's how you create that negative voltage. Now there are advantages and disadvantages to this circuit. Well, one advantage is it's pretty simple. Another advantage, which also could be looked at as a disadvantage, but it does draw current from your circuit. It needs these resistors to keep things balanced between the two capacitors here. So it's going to continuously draw current. However, if you set this thing up right, the current will be minimal. It won't be much more than the quiescent current of the op-amp that you're using. And we'll take a look at that in a demo momentarily. Now some of the disadvantages. Well, because you're using resistors to generate this center point, if you draw a DC load between either rail or the common point, for example, let's say you added indicator light right here, well, that DC current is going to pull this common point towards this rail, and that will shift your ground point. Another disadvantage is virtual ground isolation. If the power supply used here powers other parts of the circuit, its ground is this. But for your op-amp, you made the ground here, which relative to this point is 1/2 the supply voltage. So you have to separate those grounds. And because of that, another disadvantage is you have in and output coupling capacitors on your op-amp. You have to use that because if, like I say, if the power supply also powers other parts of the circuit, because of this being the virtual ground now, there'll be a DC voltage on your input and your output of your op-amp. You'll have to put capacitors on the input and the output of the op-amp so those DC voltage offsets won't affect the rest of the circuit. Now these disadvantages may not matter if your op-amp is powered with its own independent supply. For example, this preamp circuit here has its own battery power. So the rest of the circuits don't see that offset voltage because they do not share the same power supply. So there is not going to be an issue with this ground and this virtual ground. Well, this is the circuit I used in the other video. It's the third order subwoofer crossover filter. In the second video I made of that, where I did the performance, I actually used a split supply from a 9-volt battery. And I'll just use that here for this demonstration. So first I will measure the actual battery voltage. See if I can get my probes on there. Okay, so across both rails we have 7.14 volts. Yes, the battery is a little bit worn. So now let's measure from ground, which is along here, to each rail. And you can see that's negative 3.5 volts. And this positive rail will be negative or positive 3.6. A little bit of mismatch could be from the amplifier, but you know, that's not a problem. It's still very close to being pretty well evenly divided. So now I'll show you how a DC load across one of the rails will affect the balance of the virtual ground point. It won't be right in the center. So I put an LED indicator light there across one of the rails, and I will measure the voltages again. Okay, negative rail 3.12, and the positive rail 4. So it has shifted the rail voltages a little bit. Actually, it's not that bad in this case. It would still work. The only problem is if you had a large sine wave on the output of your op amp, the rail with the lower voltage would clip first. So that's why you don't want to put a direct current load on one of the rails of your supply. The second rail splitter supply we'll look at is the active type. It is quite similar to this, but we use an op amp. So what we have here is your input voltage. That's your negative and your positive. And the output of the op amp becomes the common point. So relative to this virtual ground or common point, you have your negative voltage and your positive rail. Negative rail, positive rail. Now, it behaves a lot like this circuit, except the op amp acts as a beefier set of resistors. And that will allow you to use DC loads on the output. And the amount of load you can put depends on the current the op amp can put out. There are smaller op amps that can only do a few milliamps, and you have larger ones that can do, you know, up to an amp or more. So the op amp is set up into a unity gain configuration. On the positive input, you have these two resistors going across the original power supply rails. In other words, the single power supply rails, and between those you connect the non-inverting input. So if we have a 9-volt supply here, this would be 4.5 volts. And this is unity gain, so we'll have 4.5 volts coming on the output. And if we make this the virtual ground point, we'll have negative 4.5 here, positive 4.5 here. And because this is doing the buffering here, you know, it's unity gain buffer in a sense, you can use smaller resistors that draw less current. However, you still have the quiescent current of the op amp itself. Now, one thing I should mention at this point, I am not showing the power supply rails that are connected in the power supply decoupling capacitors. In op amp circuits, those are often a given, so they're not shown here for simplicity. So don't think that I'm not actually using them, it's just not shown. Now, in dotted lines here, I'm showing an optional capacitor. This will help decouple the op amp from the power supply. So if there is some noise on the power supply rails, that will help eliminate that, though these would also help take care of that as well. So the meter just turned off. So that's why I'm showing this optional capacitor here. You know, these can be, like I say, these can be a lot higher value. Okay, I set up a little circuit here. Nice bright LED, kind of blinding the camera there, but this stuff over here is not part of it. It's just its own little circuit right here. I'm using an op amp. There's a couple capacitors on the output and the two divider resistors on the input, just like here across the power supply. And you can measure the rails. Okay, so our battery input voltage, that'll help if I get the meter in the shot, 7.35 volts. And the resistor divider network, so the half voltage point of the resistor divider network is 3.64 volts. Okay, we'll measure the output, which is now it's our virtual ground. So to the negative rail, it's negative 3.66. And to the positive rail, it's positive 3.66. And I do have a load, this LED here. It's not a big load, but it's a few milliamps. And even with that load, the virtual ground stays balanced. Now, if I did that on this circuit, that extra current, like I say, is going to pull the virtual ground towards the rail with the most load on it. Whereas this one, it stays perfectly centered. So what are the advantages and disadvantages of the active rail splitter? Well, it could have less current draw. These resistors, which are feeding the half supply voltage into the non-inverting input, these can be a much higher value than these, because it's the output of the op amp that's doing the heavy lifting, trying to keep this point centered. Now, on the other side of that, you still have the op amp's quiescent current, and depending on how the sum of that plus the current through these resistors, it could end up more than this. Another advantage, light DC loads. As you saw, even though we were drawing a light DC load across one of the rails, the output kept this perfectly centered. And again, it has to be within the op amp's current limit range for doing that. Disadvantage, well, it's more complex. You got, the op amp in the circuit where this is just passive, nothing extra here. And not shown is the power supply decoupling, for simplicity. So yeah, this is a more complex circuit. Needs more parts. Thermals. You have to watch out how much current you're drawing from the output, because the op amp can get hot if you're drawing heavy currents. So you have to, do all those calculations and things. You could be using a higher power op amp that can deliver over an amp of output, and it'd have to be on a heat sink. So that's one thing you have to consider. And there's the same issues as the passive version about virtual ground isolation, and the op amp that you're driving from the supply, you'll have to use the in and output capacitor coupling to block the DC. And of course, that all depends on if this power supply feeding this rail splitter is isolated or not. You may not need those, just like the case before. Now here's a third way we can drive an op amp with a single supply. We don't need a rail splitter circuit, but we do need some circuitry that feeds the input here. And here's what happens. We take the supply voltage, pass it through a divider network having the same value resistances. At this point, we'll have half the supply voltage, and we don't want any supply voltage noise getting into our amplifier's input. So we have this capacitor going from that point to ground. Now with our half supply voltage all cleaned up, we send it through a resistor here onto the non-inverting input. And in this example of circuit, this actually is an amplifier with gain. And if you put half supply voltage here, you're going to amplify it, but you don't want that. You want the DC gain of this amplifier to be unity. So in the feedback circuit, you have this capacitor. It blocks DC, so all the DC is fed back to the inverting input, giving the DC unity gain. Yet the AC will have gain because AC will travel through this capacitor, and this feedback divider network works properly, giving the amplifier gain. And what happens is we now have half supply voltage on the output. So that allows us to put our signal in the amplifier. The signal comes out amplified, but it's riding on that half supply voltage point. And you need that, otherwise it would clip off the bottom if you didn't offset that, because you are running on a single supply. Well, we need to get rid of that DC offset from the signal, so we use a blocking capacitor on the output, and what we're left with is a nice sine wave, and we used a single supply. So what would be a good value for the resistors and capacitors of the circuit? Well, it really depends. This op amp, again, it's the third order subwoofer filter from the other video, and it's driving a 1K load right now. So I just have it connected to this 1K resistor, and I'm outputting a very low frequency, and that's coming off the output. Now I want to see how much of that signal is being impressed on our virtual ground. Well, I was scoping the output of the filter. Now I move the probes from here to the virtual ground. Well, in the output I was getting 1.3 volts RMS, but now look at that. I'm getting signal on the output 230 some millivolts. Why is that? Well, it's due to capacitive reactance. My signal's at about 4.5 hertz, very low signal. And well, at such a low value, capacitive reactance is going to allow a voltage to appear across these capacitors. So you have to do a little bit of math to calculate the value of the capacitors. Well, we use ye olde capacitive reactance formula. 1 over 2 pi fc. Plug the numbers in. We get about 354 ohms. Well, if you remember, our output load was 1K. So there's no hard and fast rule, but I would want the capacitive reactance to be 1/10 of that when I use this op amp at its most minimum frequency. And I'd never use, in real life I'd never use a subwoofer at such low impedance, but this is just an example. So what could I use? Well, algebraic substitution, I can flip these values around, substitute and calculate the capacitance I would need for 1/10. So I flip-flopped the variables, did the math. Need a 354 microfarad capacitor. Well, it's better to step up to the next common value, which would probably be 470, for which I have. So I'll pop those in and see how that works. Okay, I popped in the 470s, and that really reduced it. Now we're down to about 58 millivolts. Now this is what the scope was set at before, so it's a lot lower. So adjust that, and yep, it really cut it down. We're only running at 4.5 hertz, and as we turn the frequency up, whoops, grabbed the wrong dial there. You can see that really decrease. I gotta turn that up now. That's 30, and it's so down to about 10 millivolts. So it really cuts down on the ripple having the appropriate capacitors. Now some people might say, well, that's still a lot of ripple on my supply. Is that going to be an issue? Well, not really, because you have to remember it's the output of the op amp itself is what's causing that. So it's not going to be an issue for that. There could be a certain situation where it would be an issue, but that's probably where you really want to go with a true dual supply. And finally, what about these resistors? Well, since we're not really drawing any DC offsets relative to the virtual ground, those can be fairly high. I'm using 4.7s. I'm trying to minimize the load on the 9-volt battery. But if you wanted a little bit more beefier supply, you could use 1,000 microfarads on each cap and 1K. The quiescent with the 9-volt battery would be, well, it'd be 2K. It'd be like 4.5 milliamps, which is, that's not insignificant, but it's still not bad. Well, that should do it for a single supply on op amps. Thanks for watching.